All right, everybody. Welcome to Chemistry from the Online World of COVID-19. Uh, Not sure if you're going to be watching this in 2022 or in some future year. So I'll just say right here and now, this is recorded on January 21st, 2022, as a second practice problem for balancing redox reactions. So basically, I'm just going to do this one, record it, so that you can pause it whenever it works for you to pause and figure out what was happening there. I'm going to be using the notes that I've been using for years in chemistry 3202. Here we go. If you have that sheet of steps by your side, I'll be referring to those. Here's the balancing reaction we're going to do. MnO2, so that's manganese, Mn. MnO2 plus bromine, Br2, produces manganese 2 plus and BrO3 with a minus charge. That's called bromate, if anyone cares. Now, the first thing we're going to do is not the optional step that I call it, optional at least, of assigning oxidation numbers. Instead, I'm going to say, okay, I'll figure out later on if this little blank is going to get labeled oxidation, and 3 or 4 lines down, if this little blank here, we move it down a bit further, is reduction. I am going to, next to these blanks, pull out the 2 halves of these reactions. I'm going to pull out the manganese half. Here we go. MnO2 reactant. I'm going to put the arrow right in the middle pretty much, and then Mn2 plus afterwards. That's the manganese half of the story. Here comes the bromine half of the story. Br2 reacts down by this blank here, leave some space, then an arrow, line it up pretty much with the other one. That's not bad. Then on the other side, the product side, BrO3 with a minus charge. Now, here we go. We have separated the unbalanced given redox reaction into 2 half reactions, the manganese half of the story and the bromine half of the story. We're now going to walk through the various steps to get each half reaction balanced. Then we're going to put the half reactions back together into a final balanced redox. Overall, the whole story back together again. All right. Now, if you're following through the notes, the sheet that I was referring to, it's step 3 that we're on here now. The first step's optional, didn't bother with it. Second step, bust separately into half reactions. Step 3, we have to go through these steps, first, second, third, and then home. Just like running the bases in a softball or a baseball game, you had to go to first, oddly enough, first. You can't go to third base or second base after hitting the ball. You have to go to first as the first thing you do. So we're going to follow these parts, first, second, third, and home in that order. The first thing you have to do, if you're reading from the sheet or if you pause and check that sheet, the first thing you have to do is balance the atoms other than oxygen, O, or hydrogen, H. All right. Let's go to our manganese half of the story. Forget the bromine half of the story for now. For the manganese half of the story, manganese is an atom other than O or H. All right. 1 in front, 1 understood to be down low, 1 manganese on the left. On the right-hand side, 1 in front, 1 down low, 1 manganese on the right. The 2 plus up high, that's the zap, that's the charge. That's not the how many of them that you have. The down low is understood to be a 1. In front for the manganese is a 1. We've got 1 manganese. Don't look at the charge up high when you're figuring out how many. As it turns out in this reaction, the manganese is already balanced. Okay, cool. Let's now go on to our other half of the story, the bromine one. So forget about the manganese story for a bit. Zooming in on this one, bromine, we're going to balance the atoms other than O or H. That means balance the bromine. That's not O or H. All right, 2 bromines on the left with the 1 understood in front and the 2 down low, 2 bromines on the left. On the right, 1 understood to be in front for the bromine, 1 understood to be down low. We've got 1 bromine on the right, 2 bromines on the left. The only way to balance out atoms like bromine that are something other than oxygen O or hydrogen H is the old school way of putting a number in front. If I put a 2 in front of here, this gives me 2 bromines on the right to match the 2 bromines on the left. I am standing at first base. I have the bromine atoms and the manganese atoms, atoms other than O or H, balanced out. Now, you're standing at first base. You want to make your way to second. How do we get there? Check what it says on your procedure sheet. The second part that we do here now is we balance the O atoms using H2O. And I'm just going to do a little aside here. Excuse my back. H2O. These redox reactions occur in a water-based, H2O-based media. Media meaning environment. So if this is a water-based environment, there's lots of H2O. H2O has O as part of the chemical formula. So O is water can be considered as a source of O atoms. All right. So thank you for coming to my TED Talk so far. The whole point of the last 2 minutes was to say we're going to balance the O atoms using H2O, and H2O is legit. All right. So back to the manganese side of the story. Forget the bromine for now. The O atoms need to get balanced. How many O atoms in the manganese on the left? 2 O atoms on the left with the 1 understood in front and the 2 for the O down low. On the right, I don't know about you, but on the right-hand side up here, I don't see any O atoms yet. So 2 O's in this half reaction on the left, no O's on the right. In order to get O's, we put H2O over here on the right. There's 1 O in every H2O. So if there's 2 O's on the left and we need 2 O's on the right, we bring in 2 H2O's. Let's do a final check here. 2 O's now on the right, 2 O's on the left. For this manganese half of the story, we have balanced the O's using H2O. Now, let's forget about the manganese side of the story for a little bit and do the same for the bromine side of the story. We're going to balance the O's using H2O. All right, let's check the left and the right for O's. On the left, no O's yet. On the right, 2 in front, 3 down here, 2 times 3, 6 O's on the right. We have 6 O's on the right. There's no O's yet on the left. We need O atoms over here. The only thing we can legitimately use in a water-based media as sources of oxygen O is water's H2O. So we put H2O in, not just one of them. 2 times 3, 6 on the right. So we need 6 of them. 6 waters gives us, for oxygen, 6 O's on the left to match the 2 times 3, 6 O's on the right. Folks, we are standing at second. We have second accomplished. We have now balanced for each half reaction, the manganese half of the story and the bromine half of the story. We have balanced the O's using H2O. We're on second. We want to get to third. How do we get to third? Check your procedure sheet. To get to third, it says balance the H atoms using H plus only. Now, why are we using H plus? Again, excuse my back. But water, we said in the acid-base unit, can be thought of as HOH, and not just HOH, H plus, OH minus. So if there's lots of water, obviously, in a water-based media, then water, think of it as H plus, OH minus, is not just a source of O's, as we saw in the last step. Water is also a source of H plus. So as we need to balance the H's now that just got into the system, we balance them legitimately with H plus. So once again, thank you for coming to my last little TED Talk there on why we're using H plus. That's the reason. Now let's do it. All right. Forget the bromine side of the story yet. We'll get there. We're going to do the manganese side of the story. To balance the H's, check for H's now on the left and right. On the left with the manganese, no H's. On the right of our manganese story, we've got 2 in front, 2 H's down low in the H2O. We got 4 H's on the right. So we're going to need H's on the left. Now, the H's have to be H plus and only H plus for the TED Talk chat that I just gave. If there's 4 on the right, we need 4H plus on the left. Cool. We now have 4 H's on the left, 4 H's on the right. For the manganese half of the story, we've balanced the H's. All right, let's put that aside for a second. Zone in on the bromine half of the story. For the H's, how many on the left and the right in the bromine half reaction? On the left, 6 in front of the H2O, 6 times 2, 12 H's on the left. On the right, there's no H's on the right yet, but we'll put some there. The H's go there in the form of H plus always. If there's 12 H's on the left, and originally there were no H's on the right, we're going to need 12 H plus put in on the right. By putting in this 12 H plus on the right, we get 12 H's on the right. To match the 6 times 2, 12 H's on the left. Folks, we're standing at third. Accomplished. We're at third. Bring us home. Don't want to be stranded on third. All right. How do we get home? Check your steps in the sheet that you've gotten from class. To get this finished, to get home, in terms of each half reaction, you balance the charge by adding electrons. So on my little side note here, I'll write down that an electron is negative charged. Now, okay, you know an electron is negative charged, but look at the minus sign there. In math, negative numbers, when you add them in with others, will only drop the total final answer down lower and lower. In other words, electrons being negative can take a higher charge and drop it down lower, but it can't take a higher charge and make it higher. Electrons are negative. It can only drop down a charge. Now, why am I saying all this? We can only put in electrons to balance out the charge. What we're going to do now is we're going to look at each half reaction on its own. And the first thing we're going to do is get the total charge on the left and the total charge on the right. Once we get that total charge on the left and right, we'll be able to compare them and we'll know where to put in the electrons and how many. Now, that's a lot of what did he just say? When we do it right now, you'll see. So we're at the home step where we have to put in the electrons. Here's how we start. We're going to do this for the manganese half the story. The heck with the bromine half the story. We'll get there in a second. So zone in on the manganese half the story. To figure out how to put in the electrons, the first thing we do is get the total charge on the left and the total charge on the right. On the left, to get the total charge, I'll take each substance individually and look at how much it brings to its total. The MnO2 has 0 charge. There's nothing written up high. So with 0 charge here, I'll put a 0 in a circle. There's no charge coming to the total from the MnO2. The H plus, okay, the H is positive. But not only is the H one positive, we got 4 of them. Make sure when you're getting the charge totals, you multiply the balancing number by the charge up high for each chemical that has a balancing number in front of its chemical formula. So for the H plus, it's not just 1 plus. We get 4 times the 1 plus. We get 4 plus contributed to the total charge on the left from these 4 H pluses. So if I get my total here now on the LHS left-hand side, 0 plus 4 is plus 4 for my total on the left-hand side. I got my total on the left for this manganese half reaction. Now I'm going to get the total on the right. On the right now, 1 in front of this Mn with a 2 plus up high. 1 times 2 plus means positive 2 comes to the charge on the right from this one of these Mn2 pluses. Water, even though there's 2 of them, water has 0 charge. So 0 charge from the water. On my RHS right-hand side, my total charge on the right, plus 2, and 0 gives me plus 2 total charge on the right-hand side. Now, once you get your total charge on the left and the right for a half reaction, stop and ask, which is the higher charge? Which is the higher total? 4 plus in this case compared to 2 plus. Okay, whichever one is the higher, that's the side that's going to get the electrons. Why? Because electrons are negative. And those negative electrons can knock down the higher charge to match the lower charge. Okay, so in confirmation, which side is higher charge? 4 plus is higher than 2 plus. So my negative electrons are going to come in on this side. Okay, perfect. How many electrons do I need to knock 4 plus total side down to equal 2 plus? 2 electrons, each being 1 minus, will now bring minus 2 from the electrons. I can get a new left-hand side total. Plus 4 was the total on the left-hand side. Now bring in 2 electrons with their negative 2. Plus 4, negative 2 gives me a new left-hand side of plus 2. Plus 2, left-hand side new total, matches plus 2, right-hand side total. I put electrons in there in the correct spot. Now, we'll just stop for a second here and realize we just put electrons in on the left-hand side, the reactant side. The definition of reduction is reactant side electrons. So this blank here that we didn't know whether to label, oxidation or reduction, RED', that's the reduction. That optional step that I said we don't need to do, put in oxidation numbers. The point of that step is to figure out what's oxidized, what's reduced. But when you get to doing the question anyway, in this step here where you're putting in the electrons, when you put in the electrons and you see it's on the reactant side, that defines the reduction for you anyway. So that optional step isn't needed because as you do the question, this is going to come out of the solution anyway. So don't do that optional step. With reactant side electrons here, this manganese half the story has to be the reduction. Cool. Now that also means in a redox reaction, you can't have 2 reductions. This bromine one is going to be the oxidation. Just watch. All right. How do we figure out if it's oxidation or reduction? Well, remember what we were doing. This is the home step. We're putting in the electrons. We got that done for the manganese. Now put that aside. Now we're doing that home step yet again, but for the bromine half of the story. Remember, we get the total charge on the left and the total charge on the right. Okay, let's do that first. Total charge on the left. Br2 is no charge, 0. Water is no charge, 0. Nothing plus nothing is nothing. I can get that correct all day. 0 charge on the left-hand side for its total charge on the left. Let's get the total charge on the right. For this BrO3, it's got a 1 minus charge, 2 in front. 2 times 1 minus is minus 2. For the H plus, 12 in front times 1 plus is plus 12. Minus 2 plus 12. For my right-hand side total, I've got plus 10. So now that we have the total charge on the left and the total charge on the right, we have to put in the electrons. We ask ourselves, which is the higher total? 10 plus versus 0, 10 is higher. The higher side is always the side that gets the electrons. How many? However many electrons we need to knock 10 plus down to match 0. That would be 10 electrons. As a check, 10 times the 1 minus in the electron would bring minus 10. We can get a new right-hand side total. Minus 10 plus 10 is our 0, new right-hand side total. That new right-hand side total of 0 matches the 0 charge, total charge on the left. We have now made it home for both half reaction for the manganese and the half reaction of the bromine. We have made it home. That step 3, first, second, third, and home is now done. Okay, cool. So catch your breath here. What we have to do now is put this back together into one redox reaction, not just 2 halves. Now, before doing that, I'm going to erase out this workspace here. Since this is a video that's being recorded, you can always go back and see this. Le voila. But I'm going to erase this out here, have a bit of a cleaner slate to work with for the next set of workers. excuse my back. Here we go. Touch up the marker there. All right. Now, the next step, step 4, says now that we have to, I believe the wording is, balance out the electrons. While we just balance the charge left and right, what we need to do now to put it back together into just one redox reaction, not two separate halves, is make the number of electrons to be equal. Now, that doesn't mean I'm going to take my 2 electrons and all of a sudden cross it out and make this 10 equal to 2. No, I'm going to actually say, okay, I need to keep the 2 electrons as they are there in that balanced half reaction, and this 10 electrons here. Oh, by the way, product side electrons, that means oxidation. Anyway, back to our balancing out the electrons. If they're not already equal, 2 is not already equal to 10, what do? We get the lowest common multiple. All right, the lowest common multiple for our electrons. What is the lowest common multiple between 2 and 10? The lowest common multiple is 10. All right, so that means we're going to multiply as needed each half reaction so that they're showing 10 electrons. We're going to take this top half reaction and we're going to multiply to get the 2 to come up to 10 electrons. Now, let's worry about our bromine half reaction later. Let's just do this one. In order to get this reaction to go from 2 electrons up to 10, the whole reaction needs to get multiplied. So we ask ourselves, 2 times what gives me 10? 2 times 5 gives me 10. This whole reaction now is going to get multiplied by 5, not just the electrons. So let's do it. For the first chemical, there's a 1 in front. 5 times 1 is 5. For the electrons, 5 times, for the H plus, I almost got ahead of myself. For the H plus, 5 times 4 is 20. Now for the electrons, 5 times 2 is 10. On the product side, Mn2 plus zap charge up high, but the 1's in front. 5 times 1 is 5. And for the water, 5 times 2 is 10. Cool. I've used up that 5 there. I'm going to cross that one outside the brackets just so that students don't think that's 2 5s still on the go there. We've multiplied through the top reaction to get our electrons up to the lowest common multiple. Now, in this reaction down here, check it out. We've already got 10 electrons. If it wasn't at 10 electrons, we'd multiply this reaction as well. But since it's already at the lowest common multiple, we don't need to multiply it any further. We're good. We now have our electron numbers equal to each other. 10 equals 10. Once you have the electrons equal, now we can get an overall reaction. Again, excuse my back. Now, how do we get the overall? Well, for starters, we can cross out the electrons that are equal and on opposite sides. Now, that's not the only thing we can tidy up here. Check it out. H2O is in each reaction. If they're on the same side of the arrow, they would add up. They're on opposite sides here. Because they're on opposite sides, they're going to cancel out. Okay, how do they cancel? Well, check it out. We've got 10 water here on the right, 6 water on the left. Whatever the lower number is, the lower number will completely cancel out. 6 on the left versus 10 on the right, the lower number is 6. The 6 water totally cancel. 10 is what we had here, cancel off 6, will leave us with 4 water molecules left to make it to the overall on the right-hand side. All right, these water molecules over here, totally got. Not done yet with what we can tidy up. The H plus, check it out. We've got H plus on the right, and we've got H plus on the left. Because they're on opposite sides, they're going to cancel out. The lower number will completely cancel. 12 on the right, 20 on the left. The lower number is 12. The 12 completely cancel. The 20 we had there on the left, cancel off 12, will leave us with 8 H plus on the left. So we've not only canceled out the electrons, we also look to tidy up any water and H plus that are present. And once we've done that, now sure enough, we can combine this into an overall reaction. So I drop down my arrow in the middle. Everything on the left makes it to the left in the overall if it didn't cancel. We've got 5MnO2 didn't cancel, plus 8H plus didn't cancel out. Cool. Plus, I'm going to move my arrow for a sec, Br2 didn't cancel. Notice that the electrons are gone, canceled. These waters are gone, canceled. So now I put in my arrow, better time for it is right there now. And with my left-hand side in, I can now bring down my right. My right-hand side, 5Mn2 plus, did not cancel. 4H2O survived to make it to the overall right-hand side. And 2 BrO3 with a 1 minus charge also made it to the overall. They didn't cancel, there they are. The H plus lost them, canceled. The electrons always cancel. You're looking at now a balanced overall redox reaction. Good job. You can actually check this. You can check the number of atoms on the left and the right. 5 manganese on the left, on the right, 5 manganese on the right. Oxygen, 5 times 2, 10 oxygen on the left. Over here, check it out. Oxygen total, 4 times 1 oxygen is 4. 2 times 3 is 6 more. 4 plus 6, 10 oxygen on the right, 10 oxygen on the left. Oh, sometimes they might be split between different molecules or ions, but they will add up and they will actually bounce out. And you can check them all if you want. The hydrogens are there as well. 8H plus on the left, 8 hydrogens on the left, 4 times 2, 8 hydrogens on the right. You can check them all, they'll all balance out. You can even check the total charge. Total charge on the left and total charge on the right in your overall also have to balance out. Check it out. On the left, no charge, 8 plus, no charge. 8 plus on the left. On the right, 5 times 2 is 10 plus nothing is still 10 plus. And then there's 2 minus. 10 plus 2 minus is 8 plus. 8 plus total on the right, 8 plus total on the left. Booyah. We got this done correctly. Now, with that said, we are not done for some of these balancing redox problems. If the question says, in base, you're actually not finished. There's one more step that you have to do. In base, you cannot have H plus present. H plus is what I call the poster boy for acid. Bronsted-Lowry, an acid donates H plus. Arrhenius, an acid dissociates H plus. So if you've got a base environment, you can't have H plus kicking around. That means you've got an acidic environment. So what do? All right, check it out. Back up here in our notes, we said H plus and OH minus together makes water. So if you've got to put your final answer in a base environment, the first thing you do is you find the H plus and you add an equal amount of OH minus. Now, just like in math class, whatever you do to one side of the equation, you have to do to the other side of the equation. So if I added 8 OH minus on the left, then I need to add 8 OH minus on the right. Now that's just going to sit there for now. That's not going to do anything where I put it on the other side. But the 8 OH minus that I just added to the left-hand side for the purpose of getting rid of the H plus, for 1 H plus and 1 OH minus, you get 1 H2O. So for 8 H plus and 8 OH minus, you get 8 H2O. The H plus and OH minus are gone now. The H plus that was causing the problem, the poster boy for acid, causing the problem in your basic environment, that's now gone. It's been converted into good old neutral H2O. Now, not quite done, but oh so close. Check it out. That H2O that you just made, realize there's H2O on the other side. 4 H2O on the other side, 8 H2O over here. This is going to get tidied up. Opposite sides will cancel. The lower number will totally cancel. The 4 H2O is the lower number. The 4 totally cancels. 8 take away 4 leaves us with 4 H2O. Our final answer is written down by just basically recopying this just neatly onto the one line. And I'll do that up here. Our final answer will look like this. All right, we've got 5 MnO2 plus. The H plus is gone. The OH minus is gone, but I got 4 H2O. That's an ugly 4. Let's get a nicer 4 for you. 4 H2O plus Br2. Arrow comes to give 5 Mn2 plus. This H2O is gone. Plus 2. Oh, I took too much space. One last fix. I'm too excited that I'm finally done my chemistry work. Can kick back for a bit. All right, just recopying it so it makes it onto the one line. 5 Mn2 plus 2 BrO3 minus plus, yeah, I had to make room for it. That OH minus that we put there to do the same thing to each side of the equation, that's crucial. That makes it to the overall because now it's still balanced, but it's balanced with different numbers from before, from when it was in acid. And if you check it out now, sure enough, this thing is balanced in terms of the same atoms on the left and the right, and the same total charge on the left and the right. Dudes, oh my gosh. All right. Thank you for hanging in there, balancing redox.